All right, we're going to go ahead. Again, my name is Steve Wilson. I'm with the Illinois State Water Survey, and I have Jennifer Wilson here with me. She was the Illinois Water Resources Center. She's also part of the private well class team. Tonight, we're hosting a webinar on how your private well works. It's meant to be the first of 3 webinars, kind of give everyone an overview of what's in the class lessons or the privatewellclass.org. I'd like to mention that this is sponsored by the Rural Community Assistance Partnership and US EPA. It's actually US EPA funding, and that went to RCAP, and they're working with us to provide this information. And so I appreciate everyone who's here, and we'll get started. Okay, so today we're going to talk about the class, private well class, which, and then what we're going to cover here, which is basically the first third of the class. Talk about a few logistics for using the webinar if you haven't done this before. And then we'll go through the materials for today and sum things up, and at the end we'll give everyone a chance to ask questions. And so going through that, the private well class is actually a set of 10 lessons that are sent as emails over 10 weeks. It's self-paced. So if you went to the website and signed up for the webinars, you saw where you could sign up for the class. Hopefully you've done that. There's more detail. There's a way to ask questions at the end. And there's a lot of resources provided for the class. And so that's the resource you should rely on down the road. The site should remain up for the foreseeable future. And there's links there to information to help answer your questions. This is the front page, or this is one version of the front page. This may actually have changed since the last time we did this. But there's a place to enroll. It lists who all the sponsors are, and you see at the bottom there it says email us at info@privatewellclass.org. If you have questions, you can always email us. We get questions from people all over the country. We can't always answer them. Sometimes we send folks back to their state agency or other groups, but it doesn't hurt to ask, and hopefully we can help you out. And now this is more earlier in the game. This class started back in January, and early on we had a lot of folks who signed up for the webinars who didn't realize there was also a set of classes that were emailed in a newsletter format out every week. And so I want to just make sure everyone realizes that these webinars are not the class. The lessons are much more detailed, and you can see on Private Well Class there's a place to enroll. And not to worry, they're all self-explanatory. They're self-enclosed, so to speak, and you'll get one a week for 10 weeks once you sign up. And it doesn't matter if you did that back in January or if you don't do it until tomorrow. So, yeah, there we are. And here's the location where you can click here to enroll. That's what it looks like. And when you register for the class, all we really ask for is your email, first name, and state where you live. And the reason we ask for state is simply to help us determine that we're reaching a national audience. And that's part of one of the things we agreed to do with this project through US EPA, is that we would reach out to all the states, which we have. And so we do ask that when you sign up for the class that you put what state you live in. And we've had a few folks from other countries and some of those things, and that's great too. Obviously this is funded through US EPA, so it's meant for a United States audience, but hopefully we're helping whoever is interested. It's all free, and so that's the idea. So there are 10 lessons. These are the first 5, and we're going to talk really about the first 3 tonight, maybe a little bit into 4. So it starts out, it's meant to be a comprehensive set of lessons. And some people don't want all 10 lessons. They want information about water quality or about source water protection or about some individual aspect of their well. Our approach to this is to help a well owner who maybe just moved out to the country or just moved into a home with a private well and has really no idea what they're doing or has learned very little about being a manager of your well. So these lessons are meant to help you become a better steward and more responsible for your water quality and your drinking water quality, and understand the responsibility you have as a well owner for protecting the aquifer that you are using for your water supply, and because that also protects the health of your neighbors and those nearby that may be using the same aquifer. And so it's important to go from A to Z to give everyone a chance to see how things work and understand how groundwater flows so that you can get into how your system works and why and where you're drawing water from and what you need to do around your well to protect it. And then if you do have water quality issues, what you can do to make your water safer to drink. And so that's what these 10 lessons are. Here's the other 5, and including emergency failures and problem solving. And, you know, we're in Illinois at the University of Illinois. We obviously can't help, we don't know everything about every aquifer in every state in the country or in every territory for that matter. And so what we can do is teach you how to find local help, what agencies in your area may have information about your well or about water quality or about treatment or source water protection issues. And so that's what Lesson 7 is all about. And again, the idea is to inform you as a well owner on what you can do to be a better steward of your groundwater source. So tonight we're covering lessons 1 through 4, or 1 through 3.5, if you will, on how your private well works. The other 2 webinars, which will be the next 2 Tuesday nights, will be about caring for your well and then water quality issues. And if you haven't signed up and are interested, please do. Again, these are kind of an overview of the material and the lessons, a little bit condensed down so they're not quite as detailed. But if you went through the lessons already, hopefully this will help you by answering a few questions you might have or by presenting it in a little bit different way, hearing someone talk about it versus what you read. And so the idea is to reinforce what's going on. So we're recording this webinar, and eventually it'll be available on YouTube. Now, we've done all 3 webinars twice before. This is the 3rd set. And honestly, I'm not 100% sure which one we'll end up using. There's no sense having 3 YouTube videos that are identical or nearly identical. And so in the end, there'll be one webinar 1, one webinar 2, one webinar 3 that's available. And I didn't change this, obviously. I left this slide. This is the 3rd time for this. And in the first sign-up set of lessons, we had a number of people sign up. And so we expected from that then to have a lot more questions. We have a smaller group tonight, so if you do have questions, you can type them in under the question box, and Jennifer's keeping track of those. We'll take a few-minute break after the end of the lesson tonight, and then I'll come back and try to answer your questions. And, I'm a groundwater hydrologist. I've been doing this a long time, 26 years, but I certainly don't have all the answers. And so if there's questions I can't answer, I'll probably ask you to email me, or we'll post it on our website and we'll find someone who can answer your question. So with that, there's the question box. If you haven't used GoToWebinar before, that little viewing box you have on the side that you can use to do things like answer a poll or those sorts of things is over here on the side. Okay, so tonight it's really about groundwater and understanding your system. And so this is going to be, the first part of this is a lesson about porous systems and about what groundwater really is. We hear all the time, well, I've got an underground river underneath my property or that sort of thing. An aquifer is a geologic unit of either consolidated rock or porous, unconsolidated material like sand or gravel that is full of water. So if I had a glass of sand and and maybe the porosity is about 30%, that means the void space or the air space in that glass is 30% of the total volume. In an aquifer, that's full of water. So the best way to describe that is if you have an aquifer that's 100 feet thick and it's a sand and gravel aquifer with a porosity of 30%, then there's about 30 feet of water there if you took all the sand away. And so the water flows through those sand grains or gravel and to your well based on pressure. Water flows downhill. And so if I put water on one end of a table and tilt the table up, it's going to run down to the other end, and that's exactly what happens in an aquifer. When you start pumping your well, you lower the water level in your well, and that makes the water level everywhere surrounding your well higher, and water starts flowing towards your well because it wants to be level. And so that's how that all works. And so I mentioned unconsolidated aquifer material. That's sand. It's also silt and clay, which aren't aquifer material, but they're other unconsolidated materials. And there's also rock. So bedrock, sandstone. In some parts of the United States where the glaciers have been, like in Illinois in the northern two-thirds of the state, you have sand and gravel aquifers above the bedrock, and then at some point you reach bedrock and there's either dolomite or sandstone or some other kind of limestone or even granite, other kinds of rock. And so in unconsolidated material, it travels between the grains, the water does, and that's where it exists in that pore space. In consolidated materials, most of those don't hold much water in the actual matrix of the rock itself. It's all in the fractures that are there. So you can see from this diagram, fractured limestone. So like Mammoth Cave in Kentucky or any other, in Missouri there's a lot of caves, and those are where water has dissolved a lot of the rock and created these springs and caves full of water. In those areas, it's called karst geology, and in those areas, the water exists in those open spaces that have been created in the rock. And the same with fractured dolomite or limestone. It's the fractures where all the water exists, and so water flows through those fractures much more readily than it does through the actual material itself. And so here's some examples. So gravel, larger grains mean water can flow through it easier. So in these examples, and this is from Texas, from their well owner manual, 300 feet to 3,000 feet a day. So water can flow through that very far, depending on the head difference, which is the water level difference between point A and point B. And as the grains get smaller, it's harder for the water to travel. And so that's why gravel and sand are considered aquifer material. Silt and clay are considered not to be aquifer material, but a clay layer is an aquitard or an aquiclude, which basically prevent water from moving very fast. Now, there's as much porosity in a silt or a clay as there is in a sand a lot of times, but because the grains are so small, water has to take a pretty treacherous path to get through them, and so it doesn't travel very fast. And so like for the clay layer, a really tight clay might move 1 foot in 10,000 years. That's not very fast. So, and with rock, limestone, sandstone, shale, and it just says rock here. It's more like granite, I believe. It depends on how old it is, how fractured it is. The one different kind of rock is sandstone. It's basically cemented sand that's been under the ground long enough that the pressure of the earth is formed it into rock. And so a lot of times sandstone will also have a secondary porosity where the water can flow through it. All the rest of these water flows through the fractures only. So here's some examples. And this is from Wisconsin's DNR well owner book. So sand and gravel, you can see water, they poured water on the top of each of these and it's moving down through. And so in sand and gravel, it kind of moves through uniformly, fairly regularly. And then in dolomite, it's flowing through the fractures. Same with the sandstone and dolomite. The fourth example here, it's two separate types of rock. And in the real world, what you'll find is when you drill a well into rock, a lot of times you may run through 4 or 5 types of layers. You might have a shale layer and a sandstone layer and a dolomite layer and then limestone and another shale. And so the water's coming from each of those units in varying degrees depending on how open they are and how many fractures they have. And crystalline bedrock is like granite. It's very solid, and typically you have very little water available. But sometimes you're lucky and you find some small fractures, and it may be enough for a home well. This example kind of shows the relationship of everything. And so at the top, you have glacial drift, it says, underneath the well on the right. And so the glacial drift is usually clay and silt mostly. It's not very permeable. All of that is saturated, and you can see the water table at the top. That's where the ground goes from being saturated below to unsaturated above. Those blue layers are sand and gravel layers. One is along a river, and there's several other thin layers where there's a well. The well on the right is in a sand and gravel unit, and those are where you find unconsolidated aquifers, and where a well would be if it's drilled into an upper sand and gravel that's above bedrock. And then in this example, there's a limestone and then a shale below it, and then a limestone and a sandstone below it, and another shale. So the shale doesn't produce water, but the limestones and the sandstone do. And so that's why they're in blue. And the confining layers, they're called, or an aquitard or aquiclude, are the gray shaded. And it shows you where there's water available and where the water isn't. And so water is kind of like oil in some ways. Sometimes you have it, sometimes you don't. There's all kinds of other issues, like, in southern Illinois, we have plenty of water in the bedrock. It's below the area that's glaciated, so it's just bedrock that's available with the water in it for a water supply. But it turns out it's all salt water. So in the southern third of Illinois, there's really no private wells or even community wells that use groundwater because there's very little fresh water available. It's salt water that was been there for millions of years, and it's just not drinkable. And so it kind of just depends. And this is from Iowa's Department of Natural Resources. So it's very similar. It's glaciated material on top to what we see in Illinois, and probably the northern tier states of the United States that have been glaciated. And so there's two types of aquifers. There's confined and unconfined. And basically what that means is whether it's open, whether it's full, for one thing. If the aquifer is completely full and it's below ground, it's confined. If it's not full and it's open to the surface, free surface, it's unconfined, which means it's the top of it, there's a saturated and unsaturated line, and where that has air above it in the aquifer material, and it's at atmospheric pressure. And so when you have an unconfined aquifer, and let's say it's sand where you live, and you drill down 40 feet into the aquifer and put it in a sand and gravel well, and you put a screen at 35 to 40 feet, but your water level is at 20 feet, then that upper 20 feet is unsaturated, and that would be considered an unconfined aquifer. Where a confined aquifer is under pressure generally, and it can also it's considered artesian, which means it's above atmospheric pressure. And what most people refer to artesian, that may be a flowing well, that's also artesian. It means the pressure on the system is strong enough to push water up through the well and have it flow out the well. And so here's an example of kind of the relationship between all these different units. And so down where the stream is in the middle, there's an aquifer there, sand and gravel aquifer, that's associated with the lowlands of the river valley. It's sand and gravel, and you can see the dashed line is the saturated line. It's usually coincident with the stream level because they're connected and water flows fairly readily. And so above the water table, that sand is dry, or it's not saturated, completely saturated. And so that's an unconfined aquifer. Whereas if you follow the dashed line up to the upper right side, the water level goes above that last layer of rock in the recharge area. And so that aquifer is confined, and you can see the direction of flow. This system, water is part of the hydrologic cycle, right? And so a lot of times when it seeps into the ground, everyone doesn't consider that part of the same system. But you can have recharge and discharge as part of that cycle with groundwater as well. And so it depends on, some of this water will seep into the ground, and a few days later will seep out, as it shows on the diagram. Other water may go deeper, and it may be decades before it actually comes out of the stream. And very deep systems get very little recharge, but the water that goes through that aquitard that's shown there to get into the lower confined aquifer, it may be flowing a completely different direction and have a much different flow system than everything else. And that water's been there for thousands or tens of thousands of years. And we've dated groundwater for studies that we've done where the water's well over 40 or 50,000 years old. And so it's been that long since it's been in there, so to speak. And so the system, when it hits the stream, it evaporates. Eventually it goes to the ocean, evaporates, gets rained again, it comes to the recharge area and starts all over again. And so a water molecule you're drinking today, may have been through this cycle 5 times or 500 times. And that's the way the system works. So this is a little bit difficult to look at, but the vertical wells all have screens. That's what the bottom horizontal lines are on each of those. There's a water table shown here, which is the line of where the water becomes saturated in the uppermost unit, and above that the soil isn't saturated. For the deep aquifer, the artesian aquifer that's shown down towards the bottom, the recharge area is up on the right side. So most geologic units, especially bedrock units, are not level. They're angled. And so, for instance, in the Chicago area, they use a deep sandstone for their water supply. A lot of communities do. And the sandstone's as much as 1,800 feet below land surface. That sandstone comes to the surface about 100 miles west of Chicago because it's on this angle. And that's the recharge area for that aquifer. And so what's happening here is the deep sandstone, or the artesian aquifer that's shown here, has its own water level. And because of the recharge that's occurring off to the right side there at land surface between the trees. And so that's shown in the artesian well and in the flowing artesian well. And the dashed line is the water level that would happen in any well that was drilled in that artesian aquifer. The water table is for the water table aquifer, which may be a sand that's connected to the stream, is the middle well, the water table well, and you can see that water level is much lower. They're really different flow systems, and in this situation, the artesian aquifer has more head, if you will. Water level is higher in wells, and so water is actually trying to go up through the confining bed to the water table aquifer and to the stream. It's being pushed in that direction because water flows downhill based on pressure. So hopefully that makes sense. And that's why the artesian aquifer has a fairly consistent water level or head. And when you drill a well in a low spot, like the flowing artesian well shown here that's in a river valley, it's very possible that the head on the aquifer is higher than the actual well elevation. And so in this case, that well would flow. There's some states like Michigan have an enormous number of flowing wells. They even have rules on how wells have to be capped so that water's not being lost. I know it's been estimated at one point they estimated before they put all their new rules in place, they were losing as much as 28 million gallons of water a day from flowing wells. And so it's a significant amount of water, it can be, depending on the situation. So this is a well diagram. It's 2 views. The view on the bottom is looking down from the top, and those lines, the 410, the 420, the 430, are the elevation of the water surface. And if you look at the top diagram, that's a slice through the ground looking at from the side. When you pump a well, and this is a water table well in this example, so it's sand and it's not quite saturated. There's a free surface, that's the dashed line. When you start pumping a well, you draw water down in the well, and then water wants to flow towards the well to level out again. And so the water table line that's flat is before pumping, and this is what happens when you pump the well, causing a cone of depression. And that cone of depression lowers the pressure, so water starts flowing towards the low pressure from higher pressure areas. And this is what it looks like. It's radial flow. If the aquifer is extensive in all directions, this will look like a concentric circles as an elevation map of the water surface. And that's radial flow to a well is how water moves. So here's an example where you have 2 wells that are pumping enough to cause overlapping cones of depression. And because there's not as much water available between the wells, as you pump both, that causes significantly more drawdown in between them, and it causes bigger cone depression overall. And again, these numbers are the elevation, and that's why the 410 is near at the wellhead itself, and it's higher as you move away. Well type. So it depends on what kind of aquifer availability you have. That usually dictates what well type you have. So when you don't have a real aquifer, let's say there's no sand and gravel units in the unconsolidated materials above bedrock, and the bedrock itself either doesn't have potable water or there's some other reason why you can't use bedrock for your water supply, then kind of the fallback is to put in a dug or bored well if you have the right type of surface geology to do that. And so it's not a real aquifer. A dug or bored well is a large diameter well that's typically, when you say dug, it means it was dug by hand. Bored is bored with a machine, 3 foot, 4 foot in diameter, that is maybe less than 30 to 50 feet deep, in some cases much shallower than that even. Water seeps in. Sometimes these are uncemented brick, those sorts of things, because you're getting water that's infiltrating into the upper soil at the surface. And so those are the last resort really for water supply, because when you're taking water from close to the surface, you're increasing your risk of having potential contaminants get in your well. So a drilled or driven sand and gravel well is a well that's in a sand and gravel aquifer. So it's cased, usually PVC or cement, and it has a screen at the bottom. And the screen is there in its size specifically to allow the water in but keep the sand out. And the entire well is cased. There's a well casing that goes all the way down to the screen. The screen has a point on the bottom, and that's so that when you pump water, you're not drawing sand in, which will ruin your pump and ruin everything else. The third type is a drilled well in bedrock, in consolidated rock. When you drill a well into rock, the rock serves as its own casing. And so you drill a well maybe through some unconsolidated material near the surface, clay, silt, maybe even a little bit of sand, and then you hit bedrock, and you drill down into the bedrock until you hit a unit that has enough fractures to provide water supply. When you seep the casing for a drilled well in bedrock, you only case it to the bedrock. Typically, you seep the casing 5 to 10 feet into the bedrock, and below that, it's all an open hole. The rock serves as its own casing. You don't need to have a casing there. You're trying to take advantage of any fractures that might be in the bedrock, and so you leave it open hole, and that provides, you should not have a lot of material getting in your well from those fractures because the rock's a solid material. It's not like sand that's going to come up into your pump and those sorts of things. In some cases you may have choices. In some cases you may have none, and that's just the way it is. I know where I grew up on a dug and bored well because we didn't have a good water supply, and it was a very old well. The house we lived in had been my grandfather's. He hand dug this well in the 30s. It was uncemented brick, 4 foot diameter, and it was 14 feet deep. And so not necessarily the safest type of water supply. In some cases, you live in an area in Pennsylvania, a lot of wells are bedrock wells, for instance, that have very low water yielding capacity, maybe a few gallons a minute. That's the only choice you have because that's the only material that's available. There's places in Illinois where you may be able to drill through 50 feet of sand and gravel and put a well in if you want, or if you decide to go deeper, there's a very good bedrock water supply as well. So you have multiple choices. The way to know what those are is to look at your well log, or if you're drilling a well, to talk to your state agency that manages well logs in your state to find out what your options are in that area. The bottom line is there's already a lot of wells in most places. And so if you look at the well logs that are available, you get an idea of what the geology is, maybe even the water chemistry if you ask the right places, and they can tell you what you're going to find in advance. And the drillers in the area will always know. They're used to drilling locally, but what you need to do is understand those differences and look that information up and have your own well log if you have a well currently. So this is an example of a bored well. It's, again, a large diameter. It's usually concrete casing or concrete tile. Old dug wells may be brick lined, as I mentioned, and so water seeps in from the water table or these maybe thin sand lenses. We've put in monitoring wells in areas where there was maybe 3 inches of sand in the first 50 feet of clay. And so we try to make a monitoring well that will work in that. It's that little bit of sand where the water is mostly seeping in. And you may have very little water. That's why you drill these large diameter so that they store. They're really a big storage basin, almost like a cistern in the ground. So here's 2 examples, and this is it's actually from Illinois Co-op Extension. In Illinois, they've changed the law now so that you have to do the example on the right. You can't have casing all the way up to the surface, and that's a safety feature. There's a minimum now of 10 feet of fill before you can have the bored well where water can seep in. And so in these 2 cases, you can see this says, I believe, 6-foot concrete tile or 36-inch tile in this example. And at each of those seams, as you go down, those are 3 or 4 foot sections. They're not cemented. They're just placed on top of each other so water can seep in at each of those seams. And in these 2 examples, they put cement along this for the first 10 feet on one side, and they filled it with earth material, usually clay, the one on the right. And so then there's a concrete seal before you get into the actual well that'll provide a water supply. And so the bottom may be open with rocks in the bottom, or it may have been filled with a gravel, or it may just be native material. So here's some examples. The one on the right is a bored well with a concrete lid. Again, in Illinois, you don't see any new wells like that because you have to have the 10 feet of material before you have the well. It looks more like the bottom picture on the left. And it's a regular wellhead that you'd find maybe even for a drilled well. And the first 10 feet is just a standpipe, basically, until you get to the bored well. And the top well is an old dug well. This is a picture I took. It's actually a well for a study we did looking at dug and bored wells and water quality from ag chemicals. And believe it or not, this well was always clean. And this is a pasture with cattle, and that's a field upslope. And it's covered with 2x12s and tin and concrete blocks. There were spiders. We opened this up, all kinds of things. And the 3 or 4 times we sampled this well, it always came back clean, which is certainly counterintuitive, and they're very fortunate. In a lot of cases, these are the problem wells. So not the best situation. So a sand and gravel well, I mentioned, has a screen. And so this is a well screen, a picture from the National Groundwater Association. It's slotted. It's called slotted screen. And the slot size is determined based on a sieve analysis of your sand and gravel, typically. Now, some drillers may have drilled 6, 7 wells within a half a mile of where your well is, so they already know what slot size to use based on that. But usually you need to size, it depends on the size of the sand grains, how fine the openings are, and how narrow the openings are. Again, that's to protect your well from having sand get through those slots and then interfere with your pump. Yeah. Here's a typical sand and gravel well. It's has a pitless adapter, which is an adapter that the water comes up to that level and then discharges into the house. It's below the frost line. And everything above that, the well cap, you have a drop pipe that holds your pump, and that allows you access. So whenever you need to do work on your well, you can take the well cap off and pull all that out by having the discharge line below the frost line. If you're in an area that has frost in the winter, it freezes in the winter, it keeps your pipes from freezing. And the old style of doing that would be to have a pit around your well. And there was no pitless adapter, so you had a pit, and there are still a lot of those in existence today. They're really a problem. If you have a well that's in a pit, you should talk to a well contractor and find out what it will take and get your well brought up to code. There's no legal reason that you have to do that, but there's a lot of safety reasons. Later in one of the lessons, we talk about abandoned wells and wells that aren't properly sealed and all the problems and safety issues with well pits. A number of people have died A lot of folks have been hurt because there's an old well pit. Eventually the house gets sold 2 or 3 times. That whole thing gets lost and people don't realize what's there. And it's really an issue. So in this case, it shows a submersible pump. When your water level is is more than 25 to 30 feet below ground surface, you need a submersible pump in your well, or well, there's a couple other types. But if you have very shallow groundwater, if your water level maybe is only 5 to 10 feet below land surface, then you're able to use a pump, maybe even in your basement, and you may have that situation because a pump can lift about 25 feet of water, and so it depends on your situation what type of pump you might have. Okay, so a sand point, I want to mention this. There's a lot of these out there. You can buy them in hardware stores in some places. When you have sand at the surface and a shallow water table, you can actually drive a sand point, which is got a screen on the bottom, and it's just a hard pipe that you can use a sledgehammer with, or something on back of a tractor, and you can drive the pipe down in below the water table to get water. There's several problems with this, and it's not illegal. In most states, it's not a legal way to put in a well. A well driller can't do this for you. You can only do it for yourself. Like in Illinois, if I want to drill my own well, I have that legal right. I certainly don't recommend that for anyone. You should use a licensed driller that's bonded, and that you have some assurance it's going to be done properly, that knows the geology of the area and all those things. When you try to do that to save money, you're messing with your health and your water supply. And in many cases, folks who have tried to do this end up having to have a driller come out anyway in the end to put in a proper well for them. And so, but I wanted to mention this because they're really not safe for drinking water. This example shows topsoil. Doesn't really say how much, but a lot of times that's not very protective. And if you have shallow sand near the surface where you put a sand point, then the topsoil is very sandy as well. So you have a lot of infiltration. So anything that's done near your well is going to seep down and get into the area where you're pulling water from. If it's in an agricultural area or an area with livestock, you're more likely to have problems with fecal contamination or pesticides or nitrate, because those things flow through sand much easier than they do a tight clay or a silt. And so they're very susceptible to pollution. That's the bottom line. And if someone wants to use something like a sand point for their garden, I think that's a great idea. Or even for, but for other things, it's not so much. Certainly anything where it's part of your potable water supply that you're drinking or using for cooking or any of those things. So a bedrock well, I mentioned before, you may, in this example, this picture, you have overburden is what it's called, and a saturated overburden. That may be a clay or a silt, or it could be even a sandy clay, or in some cases it could be even sand, but the driller, it's contaminated or has some water quality issue. West of Chicago, again, I know I use Illinois examples because that's where most of my history comes from, but west of Chicago, there's a lot of shallow sand and gravel that isn't really usable anymore because it's been contaminated. And so most of the wells go into bedrock in those areas. And so when you hit bedrock, you can see if you look at the casing, it says 10 to 20 feet of casing into bedrock, and then it stops. And after that, the hole is the open hole that was drilled with the drilling machine that drilled down into this. And the blue lines that are crosshatched here are the bedrock fractures. And the idea when you drill a bedrock well is you want to hit as many fractures as you can, because that's where the water is going to come from. And how these fractures are connected may be very well understood in an area or not understood at all. And there's cases where a farmer or a landowner may try to line up his well with 2 others he knows that get a lot of water from a certain fracture, and try to line that up maybe even a mile away, because if they can hit that fracture, they're going to have plenty of water. And if they miss it, they may only have 1 gallon a minute or some very minimal water supply. And so it can be hit or miss depending on what's going on. And in those cases, what happens with your well may influence someone pretty far away if you're in the same fracture and there's only a few wells that are using that if it's very limited. And so it's kind of interesting in a way. It's also frustrating. You can drill a well that may not produce where someone very close to you may have a well that produces enough water for irrigation, for instance, and you're using the same aquifer. Okay, so these are two other examples of a sand and gravel well and a bedrock well. It better shows there's a screen at the bottom on the diagram on the left, and you've got a water table. You're in this fine sand and gravel. There's sand lenses and clay lenses, and fine textured material means clay or silt. And you've got a pitless adapter. It goes to your pressure tank in your house. And then on the right side, you've got a board or a bedrock well that's also drilled. And you can see the drive shoe where it says that about halfway down on the right is where that's seated in the bedrock. And the fine textured material near the top, and then shale and sandstone and dolomite. Those are the aquifer materials versus the aquitard, so to speak. And so water's coming from that entire range from the drive shoe on down. It's all open hole. And so anywhere there's a fracture or there's sandstone where water can seep into the well, that's where it comes from. Okay, so this is a typical diagram for a home. It includes your well and how that's related to your pitless adapter that goes into your house, your pressure switch and your pressure tank, and how all those work. So the bottom line here is when you pump from your pump, it goes through your discharge pipe and comes to your house, and it fills your pressure tank, typically. And so your pressure tank is set to run at usually a maximum and a minimum pressure so that you have enough water pressure in your house. And when you fill the tank up until the pressure switch reaches a certain high pressure, let's say 50 psi. That means there's some storage of water in the pressure tank, and it pushes water through your house whenever you turn on a faucet. When that gets low enough, the pressure switch gets down to, say, 30 psi. This is an example. Some are set 40-60, 30-50. It just depends on your area and what you need. Then that electrical control box kicks on your pump and says you need more water in your house or in your pressure tank and in your line so that you can get the pressure back up to 50. So if you're doing several things at once, like running your dishwasher and watering your garden, your pressure tank and your well may kick on, because not only will the pressure tank not keep up, your well is actually helping push water straight through into those two uses until one of them shuts off and your pressure tank can build up enough water to get back to the 50 psi. And that's how that all works. And again, I mentioned before about the pitless unit or pitless adapter. That was a great invention, so to speak. It's just a new way. It's been around a long time now. But a long time ago, wells were installed in pits below the frost line so that your line didn't freeze if you're in an area where you have freezing issues. And the pitless adapter allows you to not have that safety hazard and still provides you with access to your pump and access to the well. Okay. Here's the other type. This is a jet pump or centrifugal pump. I mentioned earlier that whenever you have a water level that's less than 25 feet, let's say, below land surface, then a jet pump maybe even in your basement or maybe up on the surface can lift water that far. And so you don't necessarily have to have your pump in your well. And this is an example. This is an older picture from a water survey publication that shows you how that works. The centrifugal pump is on your pressure tank, basically, and it uses suction, or it's called a suction pump in some cases, to lift water into your house. And this is a piston head pump. So if you've ever used a hand pump, basically it's a piston, and that's what you're doing. You're lifting water a little bit at a time every time you pump it until finally the water reaches the surface, and then you have water for every time you pump that hand pump. Well, this pump is just using an electric motor to do that work for you. And we see a lot of these still. I would say a lot. We recently did a study where we went out and inventoried about 1,500 wells in 9 township area. And we probably ran across 30 of these. And so they still work. That's been that way for, this well may have been in place for 50 to 100 years or 80 years, let's say. The electric motor still works. The whole thing still works the way it has in the past. And so it's not ever been changed. The problem with these is you can't get in them. You can't get in your well when you have a problem. They're very difficult to get into. Some of those, when you have a problem, it would probably be a good idea to switch to a more modern type of pumping system, is the bottom line here. And here's an example of a well that's down in a pit where they've got a drop pipe there and the line going into the house. And they're just, as I said before, they're kind of a risk because it's dangerous to get in them. It's dangerous to try to service them, those sorts of things. Okay, so this is, these are 3 different pressure tanks. Initially, 50 years ago, it was a galvanized steel pressure tank, figure 3 here, where you put air in a tank and you put water in, and the air pushed the water back out into your house. The problem with these tanks, and they're not really used anymore, you don't find them to buy these days, is that the air can diffuse into the water, and eventually your bladder tank or your pressure tank becomes waterlogged, so to speak. And if you don't add air, all of a sudden your pump starts kicking on and off regularly because there's not enough air in there to cause a pressure difference. Because what you're doing when you add water to those tanks is you're compressing the air, increasing the pressure, and then it's the air that's kind of pushing the water back out whenever water is needed in a faucet or whatever. And so they require more maintenance. They can, whenever that starts to happen and they become waterlogged and there's not enough air in the tank, then no matter how hard you pump the well, you can't increase the pressure in the pressure tank to get the valve, to get the well to shut off. And so they went to these 2 other types here, and the one on the far right, the diaphragm or bladder tank, are what are used today. So you have a bladder between the air and the water that keeps them totally separated, so you can have no diffusion of the air into the tank. And then as the water comes in, it compresses the air in the bladder, and that increases the pressure to a point where then when it reaches its desired level, say 50 psi, it shuts off. It's a much better system, requires much less maintenance. You may have never had to do any kind of work to your bladder tank, your pressure tank in the past. It may have worked well for you for the last 10 years or longer even. So it's a much better system. And when you have a problem, let's say your pump starts kicking on and off much more frequently, then what's probably happened is you've got a leak in your bladder or some kind of holes, or it's been there long enough. It's usually rubberized in some way, and those can get old and brittle in a way, and eventually will go bad, and you'll start to see that. That means you probably have a leak and you're getting water up into your bladder. All right. I guess at this point we don't have any questions. So if anyone has any questions they'd like to ask, please do. And that's where we sit. So the other thing you can do is if you think of a question later or have something you'd like to talk to us about but not necessarily post here, you can go to info@privatewellclass.org, send us an email, and we can get back with you if we know the answer or find someone in your area to help you if we don't. So at this point, we'll wait a minute or two here. All right, we've got one question, and so I'll try to answer that. And then if anyone else has any, that'd be great. But the first question we got is, what is the best type of wellhead protection? Now we cover that in some of the lessons, and it would be in actually the next webinar. But it really depends on your situation. There's a lot of things you need to do to protect your well. You need to be aware of where your well sits on the landscape. Is it prone to flooding or other risks? Is the wellhead actually properly protected as far as the type of cap you have on and what you store near your well, all those sorts of things. And, there's a complete list and an approach to take to wellhead protection. Knowing what your neighbors are doing, where your septic is, all those things matter. And especially if you're in a rural subdivision, your septic may be down gradient of your well as far as where the aquifer is, but that may mean that your neighbor's up gradient well and septic are still up gradient of you. And so it's about awareness and knowing what your neighbors do, what type of soil type you have near your well, how prone is it to infiltration, all those sorts of things. As far as the best type, it really depends on your situation. I mean, really for everyone, wellhead protection and all those things matter. Making sure that there's no, you should inspect your well, for instance, to make sure that the cap and everything are sealed properly. All the pieces are in place. There's a screen on your vent tube. Make sure that's in place. There's a lot of little things to do to properly protect your well from at the surface. So I recommend, if you haven't been through the lessons, that there is, I can't remember which one exactly, but it shows a diagram from, I know, the Minnesota Department of Health that lists all the possible things that could affect your well. Even having your well away from a building. We run into wells that are in somebody's basement, or they put their garage over the well and the well's buried under cement now. Those sorts of things won't allow you to do any maintenance and on your pump, or when something fails, your well's probably just going to have to be replaced. And so there's a lot of things to look at regarding that. Okay, we've got a few other questions. I need to, give me a second here. We didn't have any questions, so I'm going to pause for 1 second and pull up a list of the questions that Jennifer's created for me. All right, so occasionally our water turns a light yellow coming out of the tap, and the color may vary from normal to light to darker yellow in different taps around the house. What could cause this? What should I do? I have heard of this. There's a community that has that same problem, and I'm trying to think, I will, if you would email us, I will find an answer for you. Where I work, we have a chemistry group that helps folks with getting their water tested and help them determine if they need treatment and some of those things. And I know this is an issue. I don't think it's a water quality issue. I think it's more of a, it's just it looks light yellow, and it's, kind of unnerving to drink water that's light yellow. Many times it's not something you can taste or see or even feel that is dangerous. Your water may look perfectly fine, and it may be very contaminated with, arsenic or some other thing. I do know that, the best I can do is if you email us, I will get you an answer, and I'll send it to our chemist because I cannot think of what it is. All right, and discussing this with Jennifer, there are other things that could be too, corrosion in your pipes, some other things. So what I'm going to do is, if you will email me, I will get an answer for you that someone who knows more than I do about this. Treatment's not a lot of my experience, and contamination issues or water quality issues, I'm much more on the water source side. And so if you'll email us, I will get you an answer. And one of the things we haven't done yet, but we will do before these webinars are all through, is all the questions we've got from all the webinars will be posted on our website with the answers. And so eventually we will get to that and get all that stuff up there. So the wellhead protection question in a rural area. Now, your pitless wellhead sits on a slope. How much of a slope is too much? It's not necessarily the slope. It's about, especially, it just means that you can have runoff towards your well. So it's important, to have the ground mounded around your well so that water runs away from it. If you're on a slope that's in a low-lying area where it might flood, that's obviously a problem. Anytime your well gets flooded, you'd need to have it tested for bacteria. So, I don't know that there is too much slope per se. It kind of depends on where it's at on the landscape. So, and, should you contact your well owner to inspect your well annually? The National Groundwater Association certainly recommends that. If you have a good relationship with your driller, or you have a driller that you know in your area that others recommend, then it certainly can't hurt. One thing you should do annually is have your well tested. Not for a complete suite of things, but for coliform bacteria and nitrate. They're good indicators that there's a pathway into your well, and there's a few other things you should test every 3 to 5 years just to be safe. It's amazing how many people have never sampled their well or had their well tested. I grew up on an old dug well, and I know we didn't test our well until my folks were trying to sell our property. And we drank it. I drank it my whole life. And it had things in it. It did. So that's probably one of the most important things you can do, because it's an indicator there might be a problem. And as far as inspecting your well annually, there's things you can do yourself. You certainly, it's probably worthwhile to have your driller inspect your well if you're inclined to do so. What are some of the methods of shocking or cleaning different wells, drilled versus dug wells, steel casings versus wood or brick? We talk about that later, and if you've taken the class, it's in the lessons. I am going to talk about that in that webinar a little more. You should chlorinate your well when it needs it, and there's a lot of different ways to go about that. As far as different states, for instance, may have a pamphlet or a booklet that describes how they would recommend it. Some of those are actually good and some aren't so good. And so what we've done is we've looked at a lot of those things from different states, and we chose what we think is one of the more comprehensive ways to go about cleaning your well. And that's also provided by the Minnesota Department of Health. We believe what they recommend and all the detail they provide not only show you how to chlorinate your well, but also talk about all the other issues that might go along with that, like making sure your pump's off and some of the safety issues with electricity that go along with that. And so, there's formulas for how much chlorine to use depending on how much water's in your well and how big the diameter of your well is and some of those things. As far as steel casings versus wood or brick, we had an issue with my well growing up, actually after I was in college, where we had, actually it was uncemented brick, as I mentioned, we had a couple frogs get in our well. So we cleaned the entire well out with a pump, contractor's pump, and then we used a pressure washer and with chlorinated water. And like I said, it was only 14 feet deep, and it's either 4 or 5 foot diameter. One of us, whether that was smart or not, my dad and I, one of us, I don't remember who, got down in the well and actually sprayed all the brick and everything. The intake, the pump intake, it's a shallow well, so we had our pump up at the top of in the little pump house we had. And we sprayed everything with chlorinated water, hoping that we had got rid of any chance of bacteria. And then you make sure the water in the well has a certain amount of chlorine, and you have to run it through all of your pipes, every faucet, every sink, every bathtub, every toilet, until you can smell chlorine, and then you let it sit overnight, as an example of what we did. But like I said, the recommendations we're using for this class are what the Minnesota Department of Health recommends for well owners. And if you go to the website and actually look at the different lessons, there's a list of references for each one of the lessons, and you'll see on that there'll be a reference under one of the later lessons from the Minnesota Department of Health about chlorinating your well, and that's what I would use. That's very thorough. So that's a long-winded answer. I hope that helps. All right. I think that's the last question. And again, if anything comes up or there's something that you're unclear of or something that I've made unclear, which is very possible, email us. We've got a lot of experts in our shop that can help, especially with the water quality side of things. And what we've done in the past is run that by our lab guys and our water chemistry folks and have them contact folks back if it's appropriate. So I appreciate everyone who showed up tonight, and thanks again.